Thank you, Christophe, for the introduction. I would like to start by thanking very sincerely the organizers. The best way to come to terms with the premature departure of one of us is to gather to celebrate his memory. And this is exactly what this conference is allowing us to do, and I'm very glad for that. I have been given the humbling task of giving an account of Jan's life work. Before I try to do my best at this, I would like to share some personal memories of Jan. So, looking back at my archive, I noticed that I met Jan actually in October, so exactly 21 years ago this month. At the time, and under the pernicious influence of Pierre Colmez, he's here, and Jean-Benoît Bost, I was sneaking out of my undergraduate classes at École Polytechnique to attend every Wednesday Jan's graduate course on elliptic curves in Jussieu. 1 year later, I actually formally enrolled in his course, so I attended the lectures once again. And there were people in the classroom with me, and with names that you would know. So if I recall correctly, with me were Maria Carrizosa, Francesco Lemma, Vincent Piloni, Jérôme Poineau, and Benoît Straub. At least. I might have forgotten people. And a couple of weeks after the beginning of his graduate course, so another month of October, 20 years ago, I asked Jean-François Mestre if he had any recommendation about choosing a master thesis advisor and a potential PhD advisor. And he recommended I learn about Euler systems, and then I should go and see Jan. So that was good advice, and so I did just that. I went to see Jan, and I told him that I had read Gross's survey on Euler systems, and I asked him if he would agree to supervise my master thesis. And he looked at me with a very wild smile that I can only characterize as at least slightly mischievous. And then he said, "Oui, j'ai un sujet." And I have been Jan's student ever since then. Now, I will not lie and pretend that this was always easy. Jan was a mathematician of extreme scientific integrity, and he had very high standards for himself. So everything should be proved in complete details. Technical simplifying hypotheses were anathema. If there were no conceptual reason for the proof not to go through, the proof should go through. So no simplifying assumptions. Black boxes were, of course, complete heresies. And at the same time, complete conceptual clarity should always be preserved. So you should be able to explain the conceptual idea of the proof in one sentence. Otherwise, this is not a valid proof. I could very, very rarely live up to these standards, maybe ever. In fact, Jan once complained that supervising my PhD had a straining effect on his finances because he was wasting too many red pencils reading my work. I have the email if you don't believe me. And I admit that I shudder a bit at the number of red pencils he would be preparing now if he knew that I was going to give an account of his work. And nevertheless, that's exactly what I will try to do. So the title of my talk is Hidden Symmetries in the Life Work of Jan Nekovar, based on his paper Hidden Symmetries in the Theory of Complex Multiplication. And I will start exactly where I started with him and because of him exactly 20 years ago, and that is to say with Euler systems. More precisely, I will start by talking about his paper of 1992. And so here is the setting. We are looking at E, an elliptic curve, on the affine modular curve of full level n. And this elliptic curve E has a complex multiplication by the order z plus n OK. N is some integer, and the k is a quadratic imaginary field. I'm going to take the simplifying assumption that this is square root minus d. Of course, he doesn't in the article. The setting is more general than what I wrote. And because E has complex multiplication, n square root of minus d is an endomorphism on E. So this means that one can consider a cycle ZE inside the Néron-Severi group of the product of E with itself, which is the image of the graph of the endomorphism multiplication by square root of minus d. And yes, thank you. Well, okay, yeah. Thank you. And so if I were to stop here, so I think that I'm too tall to use this one, so I have to. If I were to stop here, this would give me a Higner point. But Jan, who was one of the first people to, well, I don't know the first people, but who had read very closely Colley-Wegen's paper when they came out, he suggests that we should take R minus 1 product of this cycle inside the 2R minus 2 product of the elliptic curve with itself. And this yields a cycle of codimension R on the Kuga-Sato variety of full level n and the 2R minus 2 Kuga-Sato variety, or its desingularization considered by Deligne and constructed by Tony Scholl. So I don't know if you already knew Jan at the time, but reading the paper, it's very clear that he knew very well your paper, for sure.
A year before.
Okay. And so this is what we could now call a Higner cycle. And of course, the idea was generalized a lot in subsequent decades, but at the time it was brand new. And okay, so this depends on the choice of n. So this is the nth cycle, and you have a cycle of codimension R. So you can look at this image through the class map. It lands in the kernel of the class map. So there's an Abel-Jacobi map from that kernel to absolute cohomology, and then through the spectral sequence, you can land in Galois cohomology. So in this process, you get a class Zn, which lives in the Galois cohomology of the ring class field of conductor n, of the Piadic et al. Realization of the Kuga-Sato variety. So this is where the Galois representations attached to modular form of a weight 2R live. This is H1. This is H1.
H1.
Yes. Yes, because you have the spectral sequence. You make it bigger, H1?
Yes.
Yes.
W sub what?
Et al. P. So the Piadic et al. Realization. Okay, you choose a prime P. There's a motive attached to this Kuga-Sato variety, and you look at this Piadic et al. Realization.
And which work you said that he read with?
This motif was constructed by Tony Scholl in 1990. Well, I believe the paper is from 1990. Correct? No. Yeah. So if you want, then on this p-adic space, there's an action of Hecke operators, and you can, at the price maybe of extending scalars a bit, you can cut out the Galois representations attached to modular forms of weight 2R. And so if you want, you can project these classes to the Galois cohomology of Galois representations attached to modular forms. And your observation, I mean, not the observation, but Jan proved that these classes, for some subset of n, they form an anti-cyclotomic Euler system, generalizing the Euler system of Heegner points constructed by Kolyvagin. And he proved that, so that's already something non-trivial, but he did use the following theorem by the method of Euler systems. He proved that if the first class is non-trivial, so this is an hypothesis that we met several times in this conference already in talks by David Loeffler, Jala Grossi. So many people know the rest. The Tate, well, some version of the Tate-Shafarevich group attached to the Galois representation attached to a modular form occurring in this, in the étale realization of this motif. You take its p torsion part, and this is finite. And moreover,
so it is QP, the cohomology is QP coefficient?
So this is QP coefficient. And if you want to be precise, now that if you choose an eigencusp form, of course the eigenvalues can live in some finite extension. So you might want to extend slightly the coefficients. For simplicity of notation, I did not introduce this finite extension, but indeed you need to take a finite extension, and maybe this is a Gothic P above P in this finite extension, corresponding to the eigenvalues of your eigencusp form. And the image of the Abel-Jacobi map, well, if I want to take into account this finite extension, let's do it. There's a finite extension over which everything lives, and the image of the Abel-Jacobi map is actually generated by this Z1. So Z1 is a cohomology class, and so this is the image of this cycle for n equal 1 generates, if non-trivial, generates this space. So this was a theorem, and I would like to comment a bit on its novelty. First of all, at the time, I think this is the first, or really one of the first Euler systems which were constructed for modular forms outside of weight 2. And second, even in terms of the method of proof, this was one of the first time where the argument of constructing a Kolyvagin system out of an Euler system was written abstractly. One of the first, but not the first. Jan correctly remarks that already in her Bourbaki talk, Bernadette Perrin-Riou had explained how to do this in 1989, I think it was published. But still, at the time, most of this abstract machinery was new, and most of this abstract machinery he developed. In fact, experts know that this anti-cyclotomic Euler system, the distribution relations are particularly interesting when the primes are inert, above primes are inert in K. But for the sake of completeness, as he writes, Jan proves distribution relation where also the primes is split. So this has no arithmetic application in his paper, but he does it, and Sarah is laughing now because she knows what's coming. Okay, and now, okay, so this theorem, it's immediately suggests a number of questions. but the paper raises them all explicitly. So the first one, obviously, maybe, is when is the class Z1 non-trivial? Because this is the key hypothesis in the theorem. And so this is the theme of a p-adic height pairing and p-adic Gros-Zagier formula. So in 1995, Yann showed that if you were to take this class and take its height pairing, its p-adic height pairing, you would recover some p-adic L function attached to this setting. But yeah, I'm not going to discuss this, but I wanted to mention it. Another one, maybe again for experts. So in the theorem, we would expect when we have SHA, which is finite, we would expect maybe the Bloch-Kato H1f with coefficients in QP or finite extension to be of dimension 1, because that would match with the expected order of vanishing of the L function, which is, in that case, the expected order is certainly 1. But Yann proved it for the image of the Abel-Jacobi map. So a natural question is, are they the same? So is it true that the image of this Abel-Jacobi map phi is a Bloch-Kato-Selmer group in that context? And this is a theme of p-adic cohomology, symptomic cohomology, that Yann will return to much later on. Well, he will repeatedly return to in future works, but at least the question is already very clearly there in this paper. And the third question, possible generalizations. And this is the theme of Euler's system of CM points, about which he will also return repeatedly later on during his career. Now, so this was 1992, but in the mid-90s, around 1995, we can see hints of it in some survey that he wrote, and it's explicit in 1997, so that's the latest it's the latest date at which he had this idea. But so in the 1990s, he I think in the context of thinking about this p-adic height pairing and this p-adic Gros-Zagier formula, and his system, Euler system of Heitner points, he started to wonder about the following problem. Maybe I will use. So here is the problem. Suppose you have two motives or two Galois representations, and both of them have an Euler system. Then, is there a link between the Euler system of the first one and the Euler system of the second one if the motives or Galois representation are congruent modulo p? And of course, in 2023, this is an answer that has been explored a lot. But the question was, I think, relatively new at the time. And one should realize that as soon as one asks this question, you stumble upon a real problem if you expect a positive answer. So what is the conundrum? So if yes, there seems to be then a contradiction. Why? Then contradiction. And why? Because when you have an Euler system, as you can see in the theorem, some Th-Average group should be finite, and some Bloch-Kato-Selmer group should be of rank as small as possible. So when we have an Euler system, the rank of the Bloch-Kato-Selmer group should be as small as possible. So if an Euler system, if Euler systems move, for instance, p-adic analytically in some spaces, some p-adic spaces, then likewise the rank of H1f should remain as small as possible all the time. But that doesn't happen. So, but we have the phenomenon of exceptional zero. Where some Selmer group turn out to be bigger than expected. In p-adic families. So you move in p-adic families, and if you believe that Euler systems move with you, then you should expect the rank to stay small, but it does not.
So actually, what you have written before on the blackboard, I'm not in the subject, but you wrote that there is the H1F equal to image phi is just a question. I mean, why you said H1F should be as small as possible?
So are you asking about this, or are you asking about that? Or are you asking about both?
Oh, is it the same, or is it related, closer, or is it just?
Well, I mean, it is indeed related because in that setting, in other settings, it's very easy to prove that the equivalent of the image of the Abel-Jacobi map is actually H1F. Okay, but in that setting, it was not obvious by far, and Jan could prove that the image of the Abel-Jacobi map had rank as small as possible. So of course, this is closely linked to the belief that the H1F should also be as small as possible, right? So I suggest that you assume that they are indeed equal, and then you see that this theorem says that H1F is as small as possible, okay? So I mean, in many situations, even in Jan's article, it could prove that, but not in full generality, because it depends on p-adic Hodge theory, comparison theorem in p-adic Hodge theory, including in bad reduction case. And at the time he's writing, Faltings has announced a proof, but Jan rather not use it, and he's careful, so he states the strong assumption to ensure that there is p-adic comparison theorem. Okay? Right, so we have this problem. If the Euler system moves, then the rank should remain small, but we know that there is this phenomenon of exceptional zeros where the rank jumps unexpectedly. And even for Galois representations which do have Euler systems. So it's not a problem of the Euler system vanishing or whatever. So you have the problem, so what is the solution? Selmer complexes. So maybe this is my second main theme, Euler systems, and now Selmer complexes. What is the idea? As Jan explained to me how it came to him in 1997. Okay. We have seen that the Selmer module cannot move p-adically in a continuous way. But the complex can move, including its differential map. Only when the differential map vanishes, as something which moves continuously can, of course, then the cohomology groups of the complex will jump, because now you acquire a supplementary kernel when the differential map vanishes. And there you get the solution to this problem. The Euler system does move continuously. The Selmer module does not, but the Selmer complex does. So let me write down the definition of the Selmer complex, because I think that no conference for Jan could go through without this definition being written on the board. R gamma f tilde I in this notation. So you take a number field K, a finite set of place S, which would contain all places above a prime P that you fix. And you choose some Galois representation, p-adic, but it might be coefficients in QP, ZP, QP over ZP. You have a choice. And what is that? This is the cone of the complex of continuous cochain from the Galois group GKS. With value in our coefficients, whatever we have chosen as coefficients, plus the direct sum for all places in our finite set of bad places S of a complex, a local complex of local conditions. So these are cochains on the absolute Galois group of KV with value in our same coefficient. And then we go to the direct sum of the complex of continuous cochain with value of JKV. And for normalization purpose, you need to shift by -1.
So what is the CF.F?
I will, of course, tell you what C.F is. But first, I want to tell you what this arrow is. Because here you have global cochains, here you have local cochains. So you take the sum of the localization map at S, at V, sorry. And so whatever this complex C.F is, it should have a map IV from CF, the complex CFJKV, to the complex of continuous cochain. And now I will give you I will answer your question. So what is a typical example of CF? Maybe I should talk about a typical example of coefficients first. So example, maybe we want to take T, the Galois representation attached to the Tate module of an elliptic curve, but we want to do Iwasawa theory. So we base change, we extend scalars to the completed group algebra of the Galois group of some ZP power D extension. So that will typically be what you put in this line. And now what will you put? So if V does not divide P, a typical choice of complex CF is simply the short complex where you take inertia invariance, and the map is, of course, the Frobenius map, 1 minus Frobenius. So for V outside of P, you take this complex. By inflection restriction, it maps into continuous cochain. And for V dividing P, and typically you want to take as the complex the plus part in the sense of Greenberg. So maybe we're assuming that E has ordinary reduction at P. Oh. And so maybe I should say one word about this definition. It simply means that you are looking at cochains which, when restricted to JKV, satisfy this local condition or come from this local condition complexes.
So F refers to the Bloch-Kato condition.
Sorry, what?
F still refers to the Bloch-Kato condition.
Well, of course, F is intended to remind of the Bloch-Kato condition, but one thing that made Jan very sad is that the Bloch-Kato condition, strictly speaking, like the real Bloch-Kato condition with BCRIS, cannot be put into this formalism. At least at the time, and probably still now. So that's why, but of course, if your E has ordinary reduction at P, then this is very closely related to, well, I'm going to say a word about this right now. Okay. Right, so you see, in full generality, you just don't know. But this means that whatever you put as a complex of local condition, it should map into the complex of continuous cochain. Okay? So in this concrete examples, so for instance, that V at P is just the map induced by the inclusion of TV plus into T. This is a sub. This is a sub.
And understood correctly what you said, there's no way to explain this in terms of crystalline.
Well, if you put yourself in this situation, then it doesn't make sense to put down the complex defining the crystalline condition, because there's a problem of integrality and interpolating the condition. Right. Of course, we can do things much more sophisticated by interpolating the exponential map, but there's a problem of integrality anyway.
But there, you seem to suggest there's a fundamental difference between Jan.
Well, I'm not saying there's a fundamental difference. I'm saying that in full generality, we would like to put at P the condition that you and Kato put. And this does not quite work so well with the formalism in full generality. That's, yeah. Right. So this is a definition, but let me point out that in the setting of this example, we have a short exact sequence. So of course, right, so I'm going to call Hi tilde F the cohomology group of the Selmer complex. And it's fairly obvious if you check that H0 tilde F is just the usual H0, if you take these conditions. And as for H1 tilde F, there is a short exact sequence like this. So TV minus is the quotient of T by TV plus. This is the first cohomology group of the complex, of the Selmer complex. And this is the usual Bloch-Kato-Selmer group. So you see that in general, the cohomology of the Selmer complex is a strict extension of the Bloch-Kato-Selmer group. So when they both make sense, they are also different, but in an interesting way. And okay, and the reason why this is interesting is because it was observed, I don't know, in 1986 or something, by Mazotate and Teitelbaum, that this implied that the existence of an exceptional zero. So exactly the problem that we had earlier on. And 1984, thank you. Thank you. Okay, so but from this definition, this formal definition, and the formalism that Jan built around it, very natural consequences follow almost, well, formally. So first of all, you get commutative and a homological algebra properties of the cohomology group of the Selmer complex. And what am I referring to in this sentence? Well, typically, there is a problem in Iwasawa theory, which is the existence of non-zero pseudo-null submodule. So submodule of module of Iwasawa theoretic interests that are not detected by characteristic ideals. And we don't like them, and we expect that there are not so many of them, maybe that they never occur or something. But the formalism of Selmer complexes gives very short and elegant proof of the fact that they do not exist in many, many situations. So this is one thing that you get almost for free. You just, you just look at the Selmer complex and look at the Grothendieck spectral sequence attached to the composition of functors, and you get it.
It is concentrated in which range?
Oh, so you see, this is continuous cohomology of the Galois group, absolute Galois group of a number field unramified outside some finite set. So you would expect maybe 2, 0, 1, 2, but of course because you have the cone, you get 0, 1, 2, 3. Right. And I should say also that in many, many situations, but not all of them, but I'm not going to enter into details, this is a functor that maps perfect complexes to perfect complexes. So typically it will be a perfect complex concentrating in degree 0, 3, but that's not always true.
I have a question.
Yes?
So if I do the following, if I take these Selmer complexes, which can be defined actually just for the elliptic, for the Tate module,
Yeah.
and then I keep going up in the tower,
Yes.
and take a colimit of those,
Yes.
and
Yes.
then I take this,
Yes.
I get the same thing?
Absolutely.
Oh,
So this is not a trivial statement. It's also not very hard. So, Jan, of course, proves it in full generality, even for complexes of Galois representations. And so it takes him some pages in Selmer complexes, but that's absolutely true, what you said. Right. OK, so you get these properties. 2. You get perfect control theorems for Selmer modules. And by what do I mean by perfect? I mean without error terms. So what does this mean? In Iwasawa theory, we have two objects, the p-adical function and the Selmer module. And they are supposed to be equal. At least the characteristic ideal of one is supposed to be equal to the other. And the Selmer module is very easy to define. And the p-adical function should satisfy an interpolation property. So if they are equal, then the Selmer module should satisfy the same interpolation property. That's the control theorem. But typically, when you try to prove control theorem for Selmer modules, you find that there are error terms which are typically easy to bound. But you find error terms. But the machinery of Selmer complex, it really explains why there are no error terms. But the control theorem is just perfect. An isomorphism of the big thing tensor with some small ring towards the small thing. So that's something that you get almost for free. 3. You get the formalism of height pairing almost for free. And even in the derived setting. So you get derived equivalent of formulas of Perrin-Riou and Rubin. And 4, you get a duality formalism, which is again pretty formal. And this duality formalism brings us to.
Sorry, I lost the. You get these things from this extension?
Right. So what I'm saying is that once you stop thinking about Selmer modules in terms of local conditions, but in terms of the full complex with the local condition at the level of complex, and you just explore the abstract homological algebra properties of that, then you get all of these properties almost for free.
And that what you said is the top line on the left.
Sorry. No. This is just an example to show that it solves the problem of this contradiction. Because this contradiction said the H1f, your H1f, at the end of the short exact sequence cannot move p-adically. Okay? And now we have an extension which is non-trivial exactly when there's an exceptional zeros. So now H1f tilde, this will move p-adically.
And this gives us these.
No, it's these are somehow independent properties.
I see.
Yeah. It's none of them imply each other. 1 does not imply 2, 2 does not imply this extension. It's just different things which just come out of the formalism. Okay. Right, so I was writing hence ... Or what does the duality formalism on Selmer complex give you? Parity results. So this is something Jan worked on for 20 years, almost without interruption, in one way or another. Let me give you the setting. So for parity results, you want to consider M a self-dual pure motive of weight. Well, if it's self-dual and pure, it's necessarily -1. And I'm going to write V for its Piaget-Étale realization. And now there is this conjecture of Bloch and Kato. Saying that the order vanishing at S equals 0 of the complex L function of M should be equal to the dimension over QP, let's say, of the Bloch-Kato-Selmer group of the Piaget-Étale realization. And in general, I mean, if you know very well these conjectures, you would maybe have expected a minus dimension of H0 of something. But because we are of weight -1, H0 vanishes. And also maybe you would have expected that there would be some duality somewhere, because the order vanishing of the motive should be related to the dimension of the Bloch-Kato-Selmer group, the dual motive, but here we are self-dual. So we get this simplification. And moreover, because you are pure of weight -1, the factor at infinity, the Archimedean factor of the completed L function, cannot vanish at 0. But the completed L function satisfies a functional equation. And so, because the motive is self-dual, this is a functional equation relating the L function with itself. And so at 0, you just get the sign. And so, of course, this implies so this is a conjecture. And this implies the much easier, well, no, this does not imply. I'm just going to state as an easy consequence of what I said, that the parity of the order vanishing is given by the sign of the functional equation. Okay? So now here is the theorem that Jan proved in Selmer complexes, using the duality formalism for Selmer complexes. So this is from 2000, published in 2006. There's an earlier version in 2000, but let me state this version. So you take F. This is an eigen-cusp form, but Hilbert modular form. So a Hilbert eigen-cusp form. Weights are rather arbitrary, but greater than 2. And you need some technical assumptions. I'm not going to list them, and you will understand why in a few moments. Then, under this assumption, the order vanishing at S equal R. So this is the center of the functional equation for the L function of F. You find the integer R which satisfies this. You would like it to be equal to the dimension of the Galois representation attached to F twisted by R. So that would be Bloch-Kato's conjecture. And Jan proved that they are equal modulo 2. So this is already a very striking result, because this is some form of BSD modulo 2, or Bloch-Kato conjecture modulo 2. But the proof, I find, is also very interesting. And I should say that the idea of proof had a huge impact on me when I understood it. So here is the proof. Oh, sorry. I omit technical assumptions, but here I need my eigencusp form. For the sketch of proof that I will make, I need it to be nearly ordinary at all places above P. Because I want to start my sketch of proof by saying, okay, F belongs to a Hida family of p-adic Hilbert eigencusp forms. So this means that there is a family of Galois representations, and F is a point on it. And in a Hida family, you can have several branches, and maybe on an other branch, you can find an eigencusp form G, which has some nice properties. What you want of G is that it is of parallel weight 2. The level might not be the same. And in that case, now that you are in parallel weight 2, you can find a suitable K, which is a CM extension of F. So you have an Hilbert modular forms over some totally real field F. And now I'm taking a suitable extension of F. And you look at the anticyclotomic extension of K, the anticyclotomic ZP extension. So in general, this is a ZP-D extension, where D is the degree of F. And in this extension, by results of Cornu-Vatsal, but in that particular case of the thesis of Esther Aflalo, a student of Nekova, published in Aflalo-Nekova in 2007, in this setting, there are non-trivial CM points in a Shimura curve attached to this G. And using these CM points, you can construct an Euler system. And this Euler system, according to the philosophy I recalled before, so there is an Euler system of CM points for the Galois representation attached to G. Hence, when there is an Euler system, the Bloch-Kato-Selmer group is as small as it can be. So the dimension of the Bloch-Kato-Selmer group of G twisted so that it becomes self-dual is as small as it can be. So the choice of this K implies that the sign of the L function is -1. So the L function does vanish at the central point, which is here 1. And so small as it can be is 1. That's 1. But for the reason I just explained, the sign of the L function of G twisted by the Rankin-Selberg by some theta series attached to K. This is to ensure, okay, so maybe there is a tense beta here. So this is to ensure that the Euler system of CM points is non-trivial. What I just said, we have chosen K so that the sign of this the functional equation attached to this L function is -1. So this means that the order of vanishing is odd. But odd is congruent to 1 modulo 2. So the theorem is okay here, at this point. And now you want to show that this entails that it is okay there. And this is where Selmer complexes and duality formalism will play a role. Because on this family, you have a Galois representation T. And this point corresponds to T localized at some height 1 prime. And the formalism of Selmer complexes, based on this statement, shows very easily by a control theorem that the generic H1 tilde F, so the first cohomology group of the Selmer complex of T, this big Galois representation, not just this point, but this whole family, is of rank 1. But this implies that, okay, plus a control theorem, we get a short exact sequence from H1F tilde of T, which you localize at P and you mod out by P to H1F tilde of TP, which is just the Galois representation attached to F, suitably twisted, but let me, okay. And there is a co-kernel, which by simple homological algebra is just the H2 of TP, where you take the P torsion. But because our motive is self-dual, there is a Castle-Tate pairing here. So Jan showed that there is a Castle-Tate pairing here. And so just as in the usual proof of the fact that SHA is alpha the square, I mean for elliptic curves a square, you get that the contribution of this is even. So let me point out that this is an exact sequence of vector spaces of finite dimension over QP. And the dimension of this one must be even. Even dimension. This we know to be 1, dimension 1, by the previous step. So this must be odd. And now you unravel what it means in terms of sign of functional equations, because you might wonder, like, why is it always odd? But recall that we have chosen a case so that it is odd. So now you go back down to F, and you see that this remains odd if and only if the order of vanishing of the L function is odd, and becomes even if and only if the order of L function is even. And so you get the proof. In fact, after Selmer complexes, Jan developed, not alone, with the brother Dock-Chisters and also Maser and Rubin contributed, but Jan developed an industry of relative parity results in which you do not really move on such a space, but you just show a result that of the form that I indicated here. So you want to know that the parity result holds for some modular form F. You actually show it for some modular form G, which might be very different from F. For G, you do it using non-trivial CM points, and then you go back to F. And so this is the theme of relative parity results. How do we get this? So there is a skew-symmetric non-degenerate pairing on this vector space. So it's even dimensional. It's so Marc-André told me that there's a portrait of Jan that I would really like to have. Maybe Teresa, you would like to have it as well, where we see Jan smiling and saying, now we're going to do a bit of linear algebra. Is that what you're saying?
The portrait is by Esther.
By Esther, yeah.
But it's a true conversation between them.
Yes. So Jan would very often say the rest is an exercise in linear algebra. Actually, if you look at the proof of this statement in Selmer complexes, there's written easy exercise in linear algebra left to the reader. Okay, so now I don't have a lot of time left, so I just wanted to give a quick summary of further works of Jan. So first of all, you see that the existence of a non-trivial Euler system is really a key in this proof, because otherwise we wouldn't know what the statement holds here. And here we go back to the first paper I talked about, where he didn't know that his classes were non-trivial or not. And he never gave up on that. And so with Viesza-Niziol, he proved the result on symptomic cohomology, which gives indication in that direction. It doesn't prove it, but I'm not going to talk about this paper for two reasons. The first is it would be impertinent to do it in front of Viesza-Niziol. The second is that in the list of all the papers of Jan, this is almost the one that terrifies me the most. But almost, because the one that terrifies me the most is the one that Professor Goncharov, I don't know if he's still here, talked about in his talk. Oh, you're here. Which is this very old paper that Professor Goncharov explained Jan actually wrote in '87, even though it was published much later, in which Jan surmises that there is a hidden structure on metaplectic representations. And he's unable to prove that, but he proves that this hidden structure appears in the Lie algebra, at least. And 30 years later, in 2017, or maybe slightly before, he did that again. So not only did he surmise that there was a hidden structure, so that in 2007, in the paper with the same title as my talk, he surmised that there's a hidden structure on the cohomology of Shimura varieties. Hidden symmetries, yes. Yeah. And he could get it on CM points. But also around 2017, maybe slightly earlier, the publication date I think is 2017, is that correct? The Izanal paper on semi-simplicity? Yeah. 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 Obviously he knew it before, but yeah. But so 30 years after this paper, he found an argument. Okay, so now I should state this result, because this result really lives up to Jan's standard that I mentioned early in my talk. So perfect conceptual clarity. Well, I did something completely stupid now, so I apologize, but okay. And complete generality as well, and everything in full detail. So let me quickly state the theorem. So I should write. So I put Shimura in parentheses because, of course, he did something very deep with Viesza-Niziol on the cohomology of general varieties, but I'm not going to talk about. And so here's the theorem. You look at the reductive group G, which is the restriction of scalar from a totally real field F to Q of the multiplicative group of a quaternion algebra over F. And Xi is an irreducible representation of GL2 of R to the power small r. So what is this small r? So your D, I never know if it splits. I've always have trouble remembering the English term, but your D can become M2 of R, or it can become a quaternion algebra. And when it becomes M2 of R, this contributes to this small r. And so you get an area, you take an irreducible representation of that. And so here you pick a prime number, and attached to Xi and L, you get an L-adic sheaf on the quaternionic Shimura variety of level K attached to this group. And so it has a reflex field E, and you base change it to Q bar, and you take its étale cohomology. And this is a Galois representation of the absolute Galois group of the reflex field E. And there is a description of this étale cohomology by Langlands up to semi-simplification.
And Brzezinski-Labas.
And Brzezinski-Labas, thank you. Yes, that's very important. before I start the proof, I should state it. But what Jan could prove is that the Galois action is actually semi-simple. So there are complications when D is actually M2 of R, but I gloss over them. In that case, the Shimura variety is not compact, so you have to compactify and take parabolic compactification of an intersection cohomology, and then it's the same statement. And proof, I'm not going to give the details because I'm running out of time, but a wonderful idea. Using the geometry, one gets partial Frobenius morphism. And they satisfy a generalized Heissler-Shimura relations that Jan proved. And these yields many semi-simple elements in the Lie algebra of the image of rho. So what is rho? It's this Galois representation. And Jan could relate this, so then use a Lie algebra criterion for semi-simplicity. So of course I'm simplifying things horribly now, but I'm running out of time. And finally, I would like to conclude by pointing out that we have gone more or less full circle. Because now that you have this semi-simple action, it's very tempting to start exploring the plectic philosophy. And that Tony Scholl talked about in his talk. And if you believe in this plectic philosophy, then you get tons of new Euler systems again. And speaking about those, you remember that Jan said that for the sake of completeness in 1992, he would give distribution relations with split primes, for split primes, even though they have no arithmetic applications. Well, in 2022, Dimitar Jetchev, Chris Skinner, and Jan showed that they do have arithmetic applications, and he developed a theory of anti-cyclotomic Euler systems with distribution relation at split primes. And they were able to find something, do something with that. And so I think I should maybe conclude here. So thank you.
Are there questions or perhaps comments?
So, can you say a word about Jan's work on p-adic heights?
Right. So sure. So p-adic height pairings, they are typically defined on some sort of p-adic H1F. And I guess, but well, I'm not sure, that Jan got interested in them because he saw and proved that the p-adic height pairings of these Heegner cycles was giving a p-adical function in higher ways. So that got him interested into that. But very soon, I think he found, well, first of all, these p-adic height pairings, there are many, many different definitions. Some depending on splitting of extensions, so that's the way Bernadette does it. Some depending on Mazur-Tate style. And he started to, he wanted a unified setting. He wanted a unified setting. And if you try to do that in a unified setting, you immediately see that one problem will be given by exceptional zeros again. And so I don't know exactly what, well, he has a number of papers and survey in the late 90s. So you can read for yourself what he thought at the time, and you can say, he's saying, oh, but by the way, I think the correct setting is bad, and I'm announcing some results. And the upshot is that in the end, he developed the whole formalism of homological algebra for Selmer complexes, and in some sense, it follows Hyde pairings. They come with that. Like if your motive has enough supplementary structure, you get the Hyde pairing for free. Then, of course, I presented the work of Jan Nekovar, but there are many, many continuations of his ideas. And for instance, Denis Benoit, he gave a rather comprehensive treatment of Hyde pairing using local conditions at the level of Selmer complexes, but expressed as phi gamma modules. And he showed that in that context, well, I mean, this was the most general context over affinoid space. And then he showed that his construction coincided with every other previous construction. So splitting, I mean, Jan's construction in the ordinary case, splitting of extensions in the case of Bernadette's, Masertate's construction when these apply. So he has this book where each chapter is a new construction and the theorem is always the same. The construction is the same. So that's what I can say about Hyde pairing. Oh, it's a book of Denis Benoit at Asterisk, I think. And I wouldn't know the title. Maybe someone knows in the room. But there is definitely Hyde pairing in the title. Right. Yeah.
Well, I want to make a comment. I mean, maybe not about what you talked about. So thank you very much, I mean, for giving this very nice overview of Jan's work. So what I wanted to say is, even though I wasn't Jan's student, I mean, he very much influenced me, I mean, as a student. So I was a student in Cambridge, and I was determined to study Banach spaces. I wanted to become a functional analyst. But then Jan was lecturing a course on algebraic curves. And I still remember the lecture when I learned about the intrinsic group law on an elliptic curve, and at the end of the lecture it was clear that I would become a number theorist. So then, well, I went on and did study elliptic curves. I mean, sadly Jan left Cambridge, I mean, when I was a part 3 student, so I didn't have the chance to become his student. I mean, I studied with Coates. And I wrote my thesis, and then I decided to dedicate it, I mean, to Jan. So, because after all, I mean, well, I wanted to write in the dedication dedicated to Jan Nekovar, without whom I would have become a functional analyst. But Coates forbade me that. He said that was offensive to the analysts. So I didn't. So I wrote who introduced me to the beauty of number theory. So, and I gave Jan a copy of the thesis, and he just smiled. But I was very happy to learn about 15 years later that he was actually very pleased about that. So he apparently showed my thesis with the dedication to Andreas Langer. So, one other thing I remember about Jan, so he visited David and me in Exeter. And in the evening we took him out for dinner and then to a pub that David had chosen very carefully. And I remember how pleased Jan was that he could finally drink Czech beer again. I think that was one thing that he was not that happy about in France, about the quality of the beer.
Just after Sarah spoke, I thought that maybe I say a word. So when we met with Jan, this was in Moscow in '87, I actually asked him what was his development in mathematics, because I don't know about number theory in Prague. There are other subjects, but not that. And he said that I just read Sear's collected papers.
Okay. Oh God, that's what you would do, isn't it? That's what you would do.
Yeah.
Okay, so.
Further comments or recollections or what? No. All right. So, well, let's thank the end.